A warm welcome to all the viewers. In this session, I will be discussing with you the important terms of research, especially for all the beginners out there. There's a lot of confusion within the people about what is confidence interval, what is significance level, what are Z scores, what are T statistics, and how do we actually use them? What is the relevance of all these things? So let me tell you, friends, this is the foundation, this is the basics of knowing the research. You want to be a good researcher? You should be well familiar with all these basic terms. So, I'm going to explain to you all these things in a very simple and easy to remember manner with relevant examples. So stay tuned, keep watching. Now, whenever we conduct a research, we decide upon a significance level of testing the hypothesis, which is known as alpha. You must have come across that in social sciences research, we select the alpha of 0.05. That means the confidence interval, which is computed as 1 minus alpha, comes out to be 0.95 multiplied by 100, that is 95% confidence interval. Now, I have put this picture to explain this thing in a better manner. If you see, this is a normal curve. This is a bell-shaped curve. You might like to go back and check my video on empirical rule of normal distribution. So, this curve says that if I select the alpha significance level of testing the hypothesis as 0.05, that means the confidence interval will be 95%. What does it mean? It means whatever result I'll be getting, I'll be sure that it will be quite right 95% of the times. There is just a scope of error of 5%. And when we talk about normal distribution, this 5% is distributed symmetrically at the left side and the right side of the curve. So you see 2.5% on the left and 2.5% on the right. So I mean to say, if we are doing a hypothesis testing and our values lie within this curve, which is within 95%, then we say that we reject the null hypothesis and we go with the alternate hypothesis. So that means 95% of the times the results which we got will remain the same and they are inferred on the population. Now, what is this hypothesis testing critical values? You see here level of significance, as I told you, 0.10, 0.05 and 0.01. So if we are talking about 0.05 significance level, the confidence interval will be 95%, and for a left tail test, the value will be minus 1.645. So you see here, at this point it will be minus 1.645 and at this point it will be 1.645 for the right tail test. What does it mean? Now if we do a directional hypothesis testing, this is known as directional hypothesis testing. So if we know by theory that something will lead to a positive change, so we frame the alternate hypothesis in such a manner. Say The number of study hours put in by a student will lead to the increase in the marks of the student. So here we are specifying that it will lead to the increase of the marks of the student if he puts in more study hours. The number of hours a student spends on social media leads to lesser marks in the test. So here we are saying that there is an inverse relationship between the two variables, and we are going to test that through the hypothesis. So a negative relationship, a left tail test; a positive relationship, a right tail test. If we don't know the direction, whether being on social media affects the marks of the students or not, so in that case we conduct a two-tail test, and in this we specify the alternate hypothesis as there is a significant effect of mobile watching on the marks of the student. But this significant effect, is it positive or negative? We don't know. We are not certain about it. In that case, we call it a two-tailed hypothesis testing. So I hope it's now very clear to you. I have explained to you with a very simple example so that you remember forever what is a left-tailed, right-tailed and two-tailed test. And what are these values? Where do they come in this normal distribution? Because if the data is normal, we go in for parametric testing. We go in for parametric tests, right? Now, what is a critical value? We call them critical values, right? Critical values are the thresholds that represent a certain number of standard deviations away from the mean to define statistical significance or confidence intervals. So this complex statement which is written over here, I have made you explain and understand it in a very simple manner, that these numbers which you see here will correspond to this 2.5% and this 2.5%. For a two-tailed, the range is from minus 1.96 to plus 1.96. So these are known as critical values. Now let us go ahead. Now what is this? You must have come across these two formulas. This is a formula for Z statistic and this is a formula for T statistic. Now what is the difference between Z and T? If in case you have a large population, say more than 30 samples, and the population standard deviation is known to you, in that case you do a Z test. If the population standard deviation is unknown and there is a small sample that is less than 30, in that case you conduct a T test. But actually what is Z and what is T? Z distribution basically means a standardized normal distribution. A standardized normal distribution is known as Z distribution. And in T distribution, you see, when the sample size is very less, it is less than 30, then this uncertainty, unsurety of getting the right results is adjusted by taking the sample standard deviation, which you see here S, whereas in Z-score we take the population standard deviation, which is known to us. So there is an uncertainty in calculation of T-score. Because the sample size is small, we are taking standard deviation of the sample. We don't know the population standard deviation over here. So that is why there is a chance of having extreme values at the end of the normal curve. at the both ends of the normal curve. So these tails will be thicker for a t distribution curve. For a z distribution, it will be same as a normal curve, a standardized normal curve, but for a t distribution, these tails will be a little thicker because there are more extreme values. Now let us take one example to understand it. You see here, a light bulb factory claims its bulbs to have an average lifespan of 1000 hours. Here we know the population standard deviation, which is 100 hours. A quality manager tests a random sample of 50 bulbs and finds a sample average lifespan of 1050 hours. So this is the sample average. Is this difference statistically significant at 0.05 significance level? That is the alpha. Significance level is alpha. Now we know it's 0.05. Now, what is x bar? This is the sample mean. What is mu? This is the population mean, right? So in this case, the sample mean is 1050 and the population mean is 1000 hours. Then we have the standard deviation of the population, which is 100 hours, divided by under root of n, which is our sample size, which is 50 in this case, right? This is also known as standard error. In case of t-test, herein also we are comparing the means. In case of a one sample t-test, both of these are examples of one sample z-test and one sample t-test. Here we see that there is no population standard deviation given to us, it's missing, and the sample size is less than 30. So these two are the determining factors to assess whether we want to do a z-test or a t-test. Here we have 25 students. So the problem is the average time taken by the population of senior secondary students for a 100-meter sprint is 8 seconds. A researcher wants to test the effectiveness of a new training method. He then conducts a study with small sample of randomly selected 25 students and records their 100-meter sprint timing, which computes to an average of 6 seconds and standard deviation of 2 seconds. Now, in this case, we have the sample standard deviation, which is this S. We have the sample size 25. We have the sample mean and we have the population mean. Now you see here, average time taken by the population is 8 seconds. This is the population mean and this is the sample mean 6. 6 minus 8. Okay. So does the new training method significantly reduce the sprint timing? It's a one sample z-test and the t-test also is one sample. Sometimes people are confused what is z-score. So z-score is basically for a single value in a sample. Say you have taken the readings of blood pressure of a group of people and you want to standardize these values. So each value will be standardized and you will get a z-score for that. That's a standardized z-score. So you took blood pressure of say 10 people. It ranged from 100 to 140. Someone having 100, someone having 110, someone having 120. So for those 10 people, you took out the mean. For a z-score, you don't have a population mean. In this case, you will put the sample mean. And for this, you will put that particular score for which you want the z's value. Say you want it for 120. The respondent who had blood pressure 120. You put 120 minus the mean score of the sample of the entire 10 people. Whatever mean you have got, that is known as sample mean, divided by the standard deviation of the sample, and there's no need of this divided by square root of sample, because we are considering just one score. So we are standardizing that reading of 120. That is known as a z-score. So z-scores are particularly used for identifying the outliers in your data. You can go back to the playlist and check out how to check the outliers. Generally, we take a threshold of minus 3.29 to plus 3.29. If any z-score is below minus 3.29 or above plus 3.29, we call it an extreme outlier and we need to remove it from the data set before moving further for the data analysis. So this is all about z-score. I hope you got it. You got a lot of information. In case of any queries or doubts, you can always reach out to me at my mail address. Now, as you have understood what is a confidence interval, what is significance level, what is a z-statistic, a z-score, and a t-test, along with their assumptions. So, in the next video, I am going to explain to you how to conduct a one sample z-test and a one sample t-test with these two examples given over here. So stay tuned, keep watching. Thanks a lot.